So we'll go ahead and get started. Announcement about the quiz. I'm going to get that graded today. I think what I'm going to do is, like I said, the second question, part B, will be extra credit. And I know some people kind of spent a lot of their time working on that. So what I'll do is I'll probably just let people do corrections on it, on the quiz, and so I'll pass that back tomorrow. You can do your corrections and get that back to me by Wednesday. So I think hopefully that's fair. Again, sorry for problem number 2, part B. Turns out if the sum of 2 of the sides of the triangle add to the third, well, there's no way you can build a triangle that way. So for those of you that said no solution, you get extra credit. Okay. All right. So I just have one question to wrap up from 5-6. Anybody, or 5-5, sorry. Anybody need one of those handouts? Okay. So there's a section in the back, or towards the end of this section, one of the last applications of triangles is to simplify function composition. So 5.5 continued simplifying. And then when we get through this example, we'll start looking at vectors, section 5.6. So example 4. We did A kind of quickly at the end of class on Friday. Make sure you watch the video to catch the end of that. Part B, we're going to do another one. So we're going to simplify the function sine of cosine inverse of x over 2. Okay. So anytime generally you have a trig function on the outside, and then the second function in the composition is an inverse, and then ultimately the input is going to be some function of x. That's going to be the third function in the composition. And we're going to do 2 things. I didn't write it down, but we'll find the domain as well. Okay. So we should be able to simplify this function so that there isn't any trig functions appearing. And we use triangle trigonometry to do that. So let me walk everybody through this again. Okay, so if you think about the outer function sine, what do we always plug into a trigonometric function? You can always think of it as an angle that you're plugging in. Okay, so this whole cosine inverse x over 2, we're going to treat that as some angle theta. Right? And further, we're going to assume that's some angle in a right triangle. Okay? So in general, you can plug any angle into sine, but in this case, so that we can use triangle trigonometry, we're going to view theta as an angle in a right triangle. Okay, so essentially what I just did here is I made a substitution. I said all that inside stuff, cosine inverse x over 2, let's just call that theta for now. Okay. And then what we can do is we can rewrite this in terms of cosine, so apply cosine theta to both sides. And I'll get that cosine theta equals x over 2. Now, this isn't necessarily always going to be a fraction, right? The innermost function. If it's not a fraction, you can always do the divide by 1 trick. That way you can get a couple sides in a triangle. Okay. So the right triangle I'm thinking of exploiting. Let's call the bottom left angle theta. And then if you're thinking SOHCAHTOA, sine, cosine, tangent in a right triangle, cosine is supposed to be the length of the opposite side, or sorry, the adjacent side divided by the hypotenuse. So when you're looking at this x over 2 right here, you can think of the numerator as being the adjacent side to the angle. And then in the denominator 2, we can think of that as being the hypotenuse of the triangle. Okay, you all right? All right, so from here, now what we're going to do is we're going to start simplifying. So I'm going to take a step back for a second. Because sine of cosine inverse x over 2, this inside part, again, we called this theta. So this is now sine theta. And inside the triangle, or just in general, sine's always the same as opposite over hypotenuse. Okay. And then we'd like to figure out what that is in terms of x. So what we need to do is we need to find the length of this opposite side right here. Okay, so what am I going to do to find the length of that opposite side?
Op squared plus x squared equals 2 squared.
Okay, so Kirsten said we can do op squared plus x squared will equal, yeah, I can do this right here, 2 squared, right? That's by the Pythagorean theorem. Okay. So the sum of the squares of the two legs always equals the square of the hypotenuse. And when you finish solving this, what you're going to get is op is going to be the square root of 4 minus x squared. So the 2 squared is 4, we subtract the x squared, and then we take square root on both sides. And since the opposite side, if we're in a right triangle, this is supposed to be a positive quantity, so that's why we take the positive square root. Okay, so the original function then is going to simplify to, when you write this down, sine cosine inverse x over 2 is now equal to the length of the opposite side. We now know that's the square root of 4 minus x squared divided by the hypotenuse of 2. And that's our final answer. Okay. Okay, so same process every time. This inner function involving the inverse, call that some angle theta, and then convert to the original function. So in this case, cosine theta would be x over 2. That allows you to draw this right triangle with angle theta. Since cosine is adjacent over hypotenuse, we can treat the x as the length of the adjacent side, the 2 as the length of the hypotenuse. And then there's always going to be a third missing side, so you can find the length of that using the Pythagorean theorem. And then starting back at the beginning, sine of cosine inverse x over 2, since I made the substitution, that's now sine theta. And then now that we know all three sides in that triangle, we can just take, well, in this case, op over hypotenuse. And that gives us this composition of a trig function and an inverse just as a function of x. Okay, there's no trig functions anywhere in the picture. Or sorry, there's no trig functions anywhere on the right-hand side. Now, just by looking at this, you could, in a sense, find the domain from here. I think x has to be between -2 and +2. Otherwise, that square, what's underneath the square root would be a negative number. But you have to be careful. The example that we did on Friday, the outer function was tangent. Okay, so you don't want to find the domain from here in general. Okay, to be careful. In this case, it's going to work out because the outer function is sine, and the domain of sine is all real numbers. Okay, but for functions like tangent or cotangent, right, that function has asymptotes. You can't just plug anything you want it. So let me go through that process real quick. Okay, so the definition of a composition is anything that's in the domain of the any x is going to be in the domain if, when you plug something into the inside function, okay, what's in the range of that is also in the domain of the outside. Okay, so things that get spit out on the inside have to be plugged into the outside. But like I said, since the outer function is sine, it's not going to matter. The domain of sine is all real numbers. So what you can say is, I guess we can review the domain of, if it was just cosine inverse of x, this would be from 0 to pi, correct? Sorry. What did I screw up? That's not the domain of cosine inverse, that's the range. Okay, my bad. Okay, so the domain of cosine inverse, anybody remember what it was? Okay, It's the interval from -1 to 1. Okay, or that's saying that the input x has to be between -1 and +1. Okay, so the domain of cosine inverse x over 2 is, well, you have to start by setting your input greater than or equal to -1, or less than or equal to +1. I suppose I should write is given by. And then I have to solve this for x. Okay, so if I want just an inequality with x in the middle, how do I get rid of this 2 in the denominator? We can do what? Anybody have an idea? I just want an x to show up here. How do I get rid of the 2? Just multiply by 2, thank you. You might have said it, if it's soft. My hearing's not so great, so people need to speak up. So the domain is going to be, I guess, the interval -2 to 2. You can write it this way as well. Now that's just the domain of the inside function. Okay, that was just the domain of the cosine inverse. And here's where you'd have to be careful. Right? You can plug anything between -2 and 2 on the inside function. You'd have to be careful that things in the range of this function are in the domain of the outer function. But the domain of sine is all real numbers. Okay, so the domain of the original function is also -2 to 2. Which is my guess from just looking at the function on the right. Right, if I plug anything outside of this interval on the right-hand side, you're going to end up taking the square root of a negative number. Okay, again, though, the only thing you have to be careful of is if the outer function was tangent, I think we'd have to throw 0 out of the domain. Because if this was a tangent, if you plug 0, well, let me check here. What did I do in the previous one? Okay, we did arc cosine there too. If you plugged in 0 for x, you would get pi over 2. And if you had tangent on the outside, you can't plug pi over 2 into tangent. So that example we did on Friday, if you have tangent on the outside, we couldn't plug in 0 for x. So we basically had to take our interval and throw out 0. Okay. But if I'm nice and I throw sine or cosine on the outside, okay, the domain of the function's the same as the domain of what's on the inside, the cosine inverse x over 2. Okay. Announcements while I'm passing out the handout for 5-6. I think I posted all the rest of the suggested exercises as well as review exercises onto my MathLab announcements. I have the homework open for section 5-6. This time there is an online and a written. 5.5 I did not assign written homework. What's up? Yeah, the homework is due tomorrow for 5.5. The 5.6 for now I have set to be due on Thursday. I might not quite finish 5.6 by tomorrow. I might need to steal or borrow some time on Wednesday, but again, most of Wednesday will still be review. Thursday again will be review, and the exam will be on Friday. Okay. Is it okay if I erase here? So we're going to start talking about vectors. Some of you, okay, a lot of people in pre-calc are going into different places. A lot of you that are doing, say, chemistry or biology, the vectors aren't as important. Unless, my guess is, for biology and chemistry, do you have to take at least one physics here, or you don't have to? Okay, so it just depends on what you're doing. So I have to make sure I cover vectors to satisfy the physics folks, but most of you are going to go on taking calculus. You wouldn't see vectors again until calculus 3. Okay, so the third calculus class. So some of you may need this depending on if you're going into Calc 3. For those of you that are taking physics, you'll definitely need vectors. For the rest of you, sorry. It's not really much different than what we're doing before. It's all going to come down to trigonometry mostly in the end. But the main application of vectors comes in physics when you're talking about forces being applied on objects. You might want to find the amount of work done to push something up an incline. A lot of times too, you're talking about like airplanes, and you're talking about their speeds, and you have wind acting on the plane. So a lot of times the wind acting on a plane or the speed of the plane itself, all of these things can be represented by vectors. And so first off, we'll just talk definitions, if I can find them. Well, I'd look at the handout for this. Did I want this yet? Actually, I didn't want this yet. Bear with me. I'll get it in a second. So first of all, let's just read the definition on the first page. So vectors equal vectors, scalars, and the zero vector. Okay, so all a vector is, it's a quantity that has two pieces of information, a direction and a length or a magnitude. Okay, so all a vector is it's essentially an arrow that has a certain length and it points in a specific direction. We'll draw some here in a minute. With that idea in mind, two vectors are equal if they have the same magnitude, so the same length, and they're going in the same direction. Quantities having magnitude but no direction are called scalars. So like real numbers, like 5 is a scalar, right? It's a quantity that has a length but it doesn't have a particular direction. One exception is the zero vector, denoted by bold 0. The zero vector has magnitude 0 and has no direction. It's kind of a weird one. You have to define it so that things make sense. Okay, so the zero vector is just a vector that has length 0 and it has no direction. Okay, you can't really draw it either, just so you know. Okay. And then scalar multiplication. First of all, let me just draw a vector for everybody. So what a vector might look like is just going to have, a vector always has a starting point and a finishing point. Okay. Its length is called the magnitude. So one thing I can do is I can label this is the vector v. That's the natural choice for a letter for a vector. This is called the initial point. And then the tip of the vector, that's called the terminal point. And then if you like, that distance right there would be the magnitude. And of course the arrow is giving the direction it's going in. And you're going to see this later, but we denote the magnitude. It looks just like absolute value, but please don't say absolute value. Okay? Absolute value is only reserved for real numbers. And we'll talk about this notation later. The I got to learn how to spell. The magnitude is the length of the vector. Okay. So it has a length, it has a direction. You can give the vector a name, say v, and then the length of the vector v is just the same. It's the same notation as the absolute value of a real number. And then every vector has an initial point and a terminal point. Okay. Now, next definition, scalar multiplication. So you can be given a scalar and a vector u, and the vector c times u is going to be a vector whose magnitude is, well, it's the absolute value of c times the length of the vector. Let me see if I have a figure for this in the book. Okay, sweet. So I think I'm ready for this now. Okay, so again, a vector has a length. The direction in which the arrow is pointing specifies its direction. Okay, usually we use letters like U, V, W to label the vector itself. The absolute value of the vector, again, I won't say absolute value, that we really call that the length or the magnitude. And then every vector has an initial point and a terminal point. Is it okay if I cover this up or erase it? Okay. So I'm just going to get the textbook open and use some of the interactive figures here. And then we'll do a couple examples. Okay, so first thing that I want to at least make clear to everybody is these. I want to look at these two vectors right here. Okay, so first thing, notice these two vectors are in different positions. Okay, right? They're not sitting on top of each other, but they have the same length. Right? Both vectors are the same length, and technically they're both pointing in the same direction. Okay. If I was to draw a little horizontal right here, these vectors would both have the same angle from the horizontal. Okay, later on we're going to see that vectors, their direction can be described by some angle from the standard position on the positive x-axis. Okay, so vectors don't have to be in the same place to be the same vector. Okay, so again, just to get that idea, this vector v right here is the same as this vector v right there. They're the same vectors, okay, even though they're in different positions. Okay, and later we're going to talk about what's called the standard position of a vector. Usually you always place the initial point at the origin in the xy plane. Okay, so if you could shift around a vector to land on another one, they're really the same vector, even though they might be in different positions. Okay, so that's the first thing I wanted to. Now let me see. We can mess around with the length, but any way I move this around, these are all the same vectors, okay? Or they're both the same. Okay, so again, the actual position doesn't matter. As long as they're pointing in the same direction and they have the same length, they would be equal vectors. Now as for the scalar multiplication part, I just want to talk about this a little bit. So if I take a vector u, if I multiply it by the positive scalar 2, okay, the direction's going to be the same, but what have I done? I've made the vector longer, but how much longer? What's a guess? Yeah, it'd be twice as long, right? Or maybe I want to look at, let me make this longer. Okay, so again, if I take an original vector u, if I multiply it by the scalar 1/2, I haven't changed the direction, but now I've made the vector half as long. And then anybody have a guess? What if you multiply a vector by a negative scalar? It's going to change the direction. So if I say chose my scalar to be -2, hold on, I got to move this in the picture. There we go. Okay. So if I take the vector u and I multiply it by -2, the negative sign is going to change the direction, and then the 2 is just going to make the resulting vector twice as long. I don't think I can fit 3 on here, but so I can look at the vector twice as long in the opposite direction by multiplying by -2. I can take the vector u and multiply it by 1/2 to make it half as long with the same direction. And you can do this with lots of scalars. You can get on here and you can, this works with decimals. Here's a vector 0.6u, that's, I don't know how to say that this time, 6/10 as long. That'll probably work. So multiplying a vector by a scalar just changes the length, and if it's negative, it will also change the direction. Oops. So that's all I wanted to point there, just get some of that terminology out of the way. Okay, so here's what we're going to look at for example 1. So I don't have this on the handout per se, So if you're going to want to look at your answers to see if they make sense, you'd probably have to get the textbook out and look at example 1. Okay, so this is also example 1 in the textbook. And we're going to write the following vectors in terms of u and v. Okay, so here's another way to denote a vector. Okay, I won't be able to write boldface on the board for everybody. So if I write a vector in class, you're going to see me write a little arrow on top. Okay, so that lets you know it's a vector. And in particular, if you're given points in the coordinate plane like this, I can write a vector starting at P and finishing at Q. Okay, so for instance, there would be the vector PQ. Okay, so if I want the initial side to be P and the terminal side to be Q, start with P first and then Q is the second letter. Okay, so what we're going to do, we're going to write all of these vectors that I've given in example 1 are just multiples of u and v. So you have to find the scalar multiple of either of those two vectors. So what do you think if, starting at this point right here, which I'm calling the origin, I'm going 1 unit to the right? Well, if I start at P, how many units do I have to go to the right to get to Q? Just 1 unit again. So what's the difference between u and, well, I guess it told us right here. The vector PQ is really the same as the vector u. Okay. Right? They're in different positions, but they have the same direction and they have the same length. Okay. And then what about if I want to go from Q to P? What would I do instead in terms of u?
Negative u.
Okay, so part B, if I want to start at Q and point to P, that would just be multiplying u by -1. Sure, certainly QP is going to be minus u. Okay. I wonder if I can move these. Nope, that doesn't. What if I want to do QR?
QV.
Okay, so going from Q to R, you said it should be 2V, right? Because we're going in the same direction, right, on one of these little grid lines. And I'm just, instead of going 1 unit for V, I'm going 2 units to get from Q to R. So everybody said, oops, I forgot my vector arrows. Okay, so that's 2V. Let's see if we were right. I'm pretty sure we were. Yep. And then what about D? If I want to go, is it RS?
Negative 3u.
Okay, so notice to go from R to S, so you said it has something to do with U, right?
Negative 3.
Okay, so it should be negative 3u? Okay.
Do we have to add the vector arrow on top of our u?
I would prefer it, yes.
Okay.
It's going to be for your own benefit as well, because there's times where we have arbitrary scalars and vectors mixed in the same problem. So if you don't write the vector arrow, you might kind of not be sure about whether it's a number or it's a vector. And again, in the textbook, right, they're using boldface letters to note vectors, but I can't really draw boldface on the board. I've got one kind of color and that's it. Okay, so when I write vectors, you'll see the little arrow. But when you read in the textbook, all the vectors are boldfaced. And then sure enough, I think R to S was minus 3u. So it's just going in the opposite direction of u, and that would be 3 times as long. Okay. Now we're going to do vector addition and subtraction. I think I'm going to need the board again for this part, so bear with me. I'll get the projector back on in a second. Okay. So there's going to be two ways to add vectors. One is just by drawing a picture. And then later on, we're going to talk about components of vectors. They're kind of like the coordinates, right? Like points in the plane have an x coordinate and a y coordinate. Well, vectors have a horizontal direction and a vertical direction to get from the starting point to the finish point. Okay, so before we talk about components, though, I just want to talk about vector addition pictorially. Addition and subtraction. Okay. So let's say I have two vectors. So given vectors u and v, we're going to construct u plus v and u minus v. And again, the benefits of adding vectors, again, if you're in a physics class and you're working with forces, your forces are represented by vectors, and sometimes, you know, something acting on an object might be a combination of forces, so you might have to add several vectors together. Okay, so I'll draw a picture for u and v. So let's say this is u, and let's say this is v right here. Maybe I should have used a different color, but that's okay. And there's two ways to do addition. There's the triangle rule. And there's something called the parallelogram rule. Okay, so the triangle rule, if you're going to do u plus v, for the triangle rule you're going to place the initial side of v to the terminal side of u. So again, here's the vector u. And then looks like here's my vector v. And if you're going to add two vectors together, what you do is you start at the initial side of u, and you draw a vector to the terminal side of v. And that would be u plus v right there. So again, u plus v, put the initial side of v at the terminal side of u, and then you draw an arrow from the initial side of u to the terminal side of v. So again, using the triangle rule, put the terminal side, or the initial side, sorry, of the second vector onto the terminal side of the first, and then you draw an arrow from the initial side of the first to the terminal side of the second. And then there's the parallelogram rule, where this time you actually join the vectors together okay, join their initial sides together. And then the trick is to draw a copy of v and draw a copy of u to make this little parallelogram. And this time, you go from where the two initial sides meet to where the two terminal sides meet. So basically I'm just taking v and shifting it up here, and I'm taking u and I'm shifting it down there. And then to do u plus v, we start at where the initial sides meet to where the two terminal sides meet. And the reason the pictures look different is because I kind of, I eyeballed it and I didn't really draw it exactly correct. So this is geometrically how we understand how to add two vectors together. Right, if I just had two vectors on the board and I wanted to draw their sum, this is the geometric approach. Once we actually have the components, we define what the components of vectors are, we can add vectors with we can add vectors with arithmetic rules. Arithmetic rules. I can't talk today. It's okay. Okay, so right, like I said, there's a geometrical way to draw the sum or difference of vectors. I'm going to do the difference in a second, so let me take care of that real quick. For the subtraction piece, so for subtraction, if I do u minus v, we're going to again use one or the other. I'm just going to use the triangle rule. So say this is u. And then what I'm going to do is I'm going to place v. I'm going to place v like I'm going to do the triangle rule. I'm going to say v is right here. So I joined the initial side of v to the head or the terminal side of u. And here's how we're going to think about subtraction. Instead of doing u minus v, we're going to think about taking u and adding minus v to it. Okay, now, pictorially, if v is right here, minus v is just going to be the same vector in the opposite direction. Okay, so here would be, so there's minus v. And if I'm doing u plus minus v, and I'm using the triangle rule, I'll just draw it right here. So if you're doing u minus v, just draw the picture like you were going to add u and v together, change the direction on v, and then draw a vector from the initial side of u to the terminal side of minus v. Alright, so there's the geometry. Okay. There could be a question on the test where I give you two vectors and I ask you to use the triangle or parallelogram rule to draw the sum or difference or something like that. Okay. So one more example, and then we'll start talking about the components of vectors. You have to get rid of all this like geometric understanding first. Okay. So now what we're going to do is we're going to write certain vectors as sums or differences of scalar multiples of vectors. So example 2, what do I have on here? I've got 3, we've got OP, we've got OQ, and I've got QR. Okay, so just like the previous example, I've got two given vectors. I don't know why it won't let me. There. Okay. So I have two given vectors, both. This is what we call standard position when you put two vectors with their initial side at the origin. Okay, again, remember, this vector could be up here and it would still be the same vector. But generally the standard position is the origin. And then we're going to write down a few of the, we're going to write some linear combinations of these vectors. So if I want to get from O to P, right, I might have to go, you know, I might have to make the vector V twice as long and the vector W like twice as long, and I might have to add those together. So anybody know how, if I'm starting at the origin, how I can maybe get to P right here? So you can see if I want to, I have to go some length in this direction, and I have to go some length in that direction.
It would be 2W plus 3V.
Okay, so I can go 2W to get here, and then I can add the vector 3V, and then the triangle rule would say that that vector O to P is the sum of those two. Okay. Actually, maybe I can use the board to do this. Then I can actually draw on this thing. And then we can all see it better. There we go. Okay, so one thing I could do, let me get my green marker. So I could go from the origin up to here, and that would be 2W, right? Like, is that what you said, Kirsten?
Yeah, I said 2W3.
And then we could go from here to get to P, and this would actually be, well, V is going horizontally, and this is 1, 2, 3 times the length. That would be 3V. And then OP, which would just be 2W plus 3V, if I use the triangle rule. Okay, so the origin to P is 2W plus 3V. What about OQ? So I want to get from the origin to the point Q. Well, I've got to go this direction 1 unit and then 3 units to the right.
3V plus negative W.
Okay, so this is the minus W, right? And then you said you got to go this direction as well. You said that's 3V.
Can't you just do 3V minus W?
Yep, you can do it either way. Okay, so if I add those two together, that's the, you can do 3V minus W, or I'll write it over here. You can do 3V minus W, or if you like, I'll just write another equals, you can do minus W plus 3V. Okay, vector addition is commutative just like real numbers. Okay, so starting at the origin to get to Q, we had to go in the opposite direction of W once, and then we had to go 3 times the vector V to get here. And then finally I want to get from, well, this time I'm going to go Q to R. So I think what do we have to do? We have to go this direction and then go this way. So starting at Q, how many times did I go in the direction of W? Twice, so that's 2W. And then I just went in the direction of V once. And then now to CQR, it would be the vector 2W plus V if I use the triangle rule. So sorry, there's a mess up there. So basically it's just how many times do you have to go in the direction of one of the vectors plus how many times do you go in the direction of the other to get to the final point from the starting point. Is that okay with everybody? Alright. Make sure you look at these figures again. You might want to watch the video again since I didn't really have a whole lot of room for you to draw this. Okay. I think anybody still need this on the board or are we good? Okay. So last example, we're going to talk about components of vectors. So vector components and magnitude. Okay. So definition at the top of page 3. A vector v with its tail at the origin and its head at coordinates v sub 1, v sub 2 is called a position vector, or a vector in standard position. Okay, so you always put the tail or the initial side. Sorry, and I said initial side and terminal side. You could also replace that language with head and tail. Tail and head. Okay, tail is the initial side, the terminal side is the head. Okay. So again, let me grab a better marker. So you have a vector with the tail at the origin and head at the point v1, v2. That's called a vector in standard position. And in this case, we call v sub 1 and v sub 2 the x and y components of the vectors. And then what you can say in this case is that the vector v could be written like this. And instead of parentheses, we use angle brackets for vectors. And then there's that second piece. Two position vectors are equal if and only if their components are the same. Probably all I have time for today. Tomorrow I'll probably get through examples 4, 5, 6, hopefully 7 or 8. Okay, so example 3, sketching vectors. So A, we're going to sketch the vector with components 2 and 6. B, we're going to sketch the vector with components -1 and 3. And C, we're going to sketch -2, -4. Okay, so I'll draw a set of coordinate axes here. How about one with a straight vertical axis though? Close enough. And then I need to go, what, 6 units in every direction? 1, 2, 3, 4, 5, 6. Okay. So essentially what these are for is the x component's the horizontal direction you have to take to get to the head of the vector, and the second component is the vertical direction you have to go. So if I want to draw the vector 2, 6 starting in the standard position at the origin, positive 2 means go 2 right, and positive 6 means go up 6. So I'll go 2 units right, and I'll go 6 units up. And then right here, that would be the vector 2, 6.
So we're graphing them like we would any other point. We're just drawing a line.
As long as your vector's in standard position, these are just the coordinates of the head of the vector. Yep. Exactly. Now, I could have also drawn this vector starting here, though. I just would have to go 2 units right and 6 units up. Just give me the last minute here to at least draw these other 2 vectors. So -1, 3, if I draw it in standard position, I start at the origin, I go 1 unit to the left, and I go up 3 units. So there's the vector -1, 3. And then now I can go, for the last one, part C, I can go 2 units to the left and 4 units down. Here's the vector -2, -4.